Welcome to The Explainer. Today, we're going to tackle a massive idea, one that's so common we barely even notice it anymore, the idea that your brain is basically a computer. But we're going to look at some fascinating evidence that suggests this whole metaphor, well, it might actually be holding us back from understanding what our minds really are.
And we're kicking things off with this quote from the philosopher Hubert Dreyfus, because it just perfectly captures the radical shift we're about to explore. I mean, what if the world isn't something your brain just creates a little copy of inside your head? What if the world is something your mind is fundamentally a part of?
You know, for decades, the go-to metaphor for the brain has been the computer. We picture this 3-pound organ sealed up inside our skull, running this incredibly complex software that we call the mind. It's a really powerful and, honestly, a pretty intuitive idea.
And at the very heart of this metaphor is this model: sense, plan, act. It's kind of like a factory production line, right? Information comes in through your senses, your brain, the central processor, builds this detailed internal map of the world, figures out the best move, and then bam, sends out the command to the body.
But, this super neat model, it makes some pretty huge assumptions. It basically treats the body like it's just a puppet and the world is just a source of data. So today, we're going to explore two revolutionary ideas that completely flip this script and suggest the real story of how we think is far weirder and way more wonderful.
Okay, so let's dive right into this with our first big reveal, which challenges the very location of the mind. Is intelligence really locked away inside your skull, or is it something that happens in this dynamic dance between an organism and its environment?
And our first piece of evidence is surprisingly old school. We're talking about these simple but totally brilliant robots from the 1950s. A neuroscientist named Gray Walter built them, and he called them his tortoises. Now, what's so fascinating is just how simple these machines were. I mean, they had no central computer, no memory to speak of. They just operated on two basic reflexive rules. 1, move towards a gentle light, and 2, if you bump into something, turn and push. That's it.
And yet, from just those two incredibly simple rules, something absolutely amazing happened. The tortoises started showing behaviors that looked complex, purposeful, even surprisingly lifelike. They'd explore their environment, they'd find their charging station when their batteries got low, and they'd even clear obstacles out of their way.
So you have to ask, where did all that complex behavior come from? It wasn't planned inside the tortoise's circuits, no way. It emerged from the real-time interaction between the robot's simple body and the world around it. The intelligence wasn't in the box, it was in the loop.
And listen, this isn't just some clever trick for robots. Nature has been using this exact strategy for hundreds of millions of years. For a great example, let's just look at how a female cricket finds a mate.
I mean, on the surface, this looks like a serious computational challenge, right? Especially for an insect with a brain the size of a pinhead. She has to identify the exact song for her species, figure out which of all the competing males is the loudest, and then make a beeline straight for him. That sounds like it would need a lot of processing power.
But here's the genius part. She doesn't compute the answer. Her body is the answer. You see, her ears are on her front legs, and they're connected by a tube. Because of the simple physics of sound traveling through that tube, the ear that gets the first pulse of sound from a male's chirp gets stimulated just a tiny bit more intensely. This automatically makes her turn in that direction. The thinking is offloaded directly onto the physical structure of her body. It's brilliant.
Okay, so all of this brings us to our second big revelation. If thinking isn't just confined to the brain, then what exactly is the brain doing? The classic view says it's this logic machine, building a perfect model of reality. But what if it's actually more of a history machine?
So your brain faces this fundamental challenge, and it's called the inverse problem. The world out there is this rich, stable, three-dimensional place. But the raw data your brain gets from your eyes, it's a flat, two-dimensional, ever-changing, and often really ambiguous pattern of light. So, how on earth does it bridge that gap?
All right, let me show you a really powerful example of this in action. Just take a look at this image. Which one of the two central gray regions looks darker to you? For pretty much all of us, the one on the left seems obviously significantly darker than the one on the right.
Your perception is immediate. It's certain. You see a curved surface, right? Maybe it's made of concrete or stone, and it looks like there's a highlight on one side and a shadow on the other. It's a simple, clear scene.
But what if I told you they are physically identical? I mean, pixel for pixel, the exact same shade of gray. If you were to isolate them from their context, you literally could not tell them apart. So why? Why do we see them so differently?
It's because your brain isn't a passive camera just taking a picture. It doesn't see what's actually there. It sees what it predicts should be there, based on a whole lifetime of experience. Your brain is making a powerful, instantaneous bet. See, your brain is an empirical engine. Over millions of years of evolution, and over your own personal lifetime of experience, it has learned that this specific pattern of light gradients is almost always caused by light hitting a curved surface. So, it generates the perception of a highlight and a shadow, because that has always been the most useful behavior-guiding interpretation in the past. Your perception is a reflection of history, not just current reality.
So, okay, let's put these two big ideas together. If our mind actually extends out into our body and into the world, and our brain operates based on past experience instead of pure, real-time logic, what does that mean for how we solve problems and just navigate our lives?
Well, it means we don't just act to get things done, we also act to help ourselves think. We perform pragmatic acts, like hammering a nail, but we also do these things called epistemic acts. These are actions that don't solve the problem directly, but they change the world around us to make the problem easier for our brains to handle. Think about how you might arrange Scrabble tiles to try and see new words. That's an epistemic act.
And for a truly mind-blowing example of offloading cognition onto the world, we have to talk about the architect Antoni Gaudí. He was faced with designing these incredibly complex stone arches for his churches, a mathematical problem that was pretty much impossible to calculate back in the day.
So how did he solve it? He outsourced the entire problem to gravity. That's right. He built an upside-down model of the church using strings, attached little weights to represent the structural load, and just let physics do all the work. Gravity spontaneously formed the absolute perfect curves for the arches. All he had to do was photograph the result and flip it upside down. This wasn't just a model, it was his cognitive tool. And this really leaves us with a provocative final thought. The boundary between our mind, our body, and our tools, it isn't fixed. It's fluid. From a cricket's ears to Gaudí's hanging chains, we see that intelligence is a property of a whole system, not just a brain in a box. So as we continue to build this world filled with ever more powerful and immersive technologies, AI, virtual reality, constant connectivity, we have to ask ourselves, what kind of minds are we building for ourselves?